Hey students, one of the most important principles that we're going to work with this quarter is called determinism. And so we will always seek to understand determinism in every instance. Sometimes we will seek to get the best determinism we can, make it the most deterministic. Sometimes it won't be so important, and it just depends on the application, but we always need to be aware of where determinism stands, because we need to understand it for every application. So let's look at this. So when we are trying to locate something, the thing that we need to do is we need to isolate 6 degrees of freedom. Remember, we have 3 translations along the orthogonal directions, and then we have 3 rotations around those orthogonal directions. Now we actually have 12 directions of motion, because we can go in plus x or minus x, plus y, plus z, minus z, and we can rotate clockwise and counterclockwise around each of those rotations. And so what we need to do is we need to isolate the degrees of freedom, and we use locators to do that to begin with, and that limits the degree of freedom, and usually it only limits it in one direction, not always. And then we often use a clamp directly across from the locator to eliminate that second degree of freedom. Why don't we use clamps on both sides? Well, the idea here is that a locator is a fixed device, so that its location in space stays constant, and a clamp is a movable device. And so if you have a workpiece that is different thicknesses sitting on this locator, the clamp takes up that tolerance in thickness, but the locator stays in location. And so we need to talk about how would we eliminate those degrees of freedom. And so in any instance, we just need to understand and count for the degrees of freedom being removed. When you read the book goes through and it has all these categories of workpieces and these categories of ways that you might locate them, and it tries to draw these lines between them. But I don't think that's really a healthy way of doing it. Instead, what I think we need to do is we need to just focus on determinism. So determinism says, or what it is defined as, is something is deterministic if it can be, its occurrences can happen in accordance with natural laws. Well, what does that mean? What that means is that you can calculate it, or to put it more succinctly, there is only one solution. And so a fixture design is deterministic if the part can only be in one location on the part. And so we'll look at that in just a second here and see a little bit more about what that means. But we want to cause the contact to happen at chosen locations, not just happen by chance. We want to determine where those contact locations are, and we want to know how it's going to contact the part as well. Okay, so let's do that. All right, so if I have this plate and I want to fixture it on this big plate, I could take it and I could just set it on there. And we could say, how many degrees of freedom does that remove? And a plane on a plane, well, it looks like it won't move down anymore. So we've eliminated the z axis of motion. And remember, we've just eliminated it in one direction. It could still come up, but we will call it eliminated because we could always put a clamp on it, and that would hold it against this, and then we would have eliminated both up and down. So 1 degree of freedom. It turns out that it also can't rotate around this axis or around this axis anymore when it is down on the part. So it has eliminated 3 degrees of freedom. What 3 does it still have? It can slide in y, it can slide in x, and it can rotate around z. So we've eliminated 3 degrees of freedom, but it is still but we've still got 3 degrees of freedom. Okay, so what we need to know is, do we we eliminated 3 degrees of freedom when we put these two together. But do we know really where these are contacting each other? I just have a flat-ish side here, but it's, I mean, it's not totally flat. You can potentially see there are tool marks on there. There's the word side 2 is on there. It's also had these holes drilled through it, so depending on what side those came from, they may have burrs. It's got some scratches over here because it's been used in lab. So I don't really know if that's flat. And then this piece right here hasn't even been finished, and so I'm pretty sure that this isn't flat. And in fact, at a microscopic level, they are not flat at all. You can guarantee that the two of them are not flat. And so a plane touching a plane mathematically, they will contact in 3 locations. What 3 locations? Well, right now, I don't really have any idea. I could do a microscopic mapping of this surface, and then I could do a microscopic mapping of this surface, and I could figure that out. In machining, the way that they do that is they cover this with a thing called bluing, which is just sort of ink that goes on there, and then you put this part down, and you might move it around just a little bit, and then you pick it up and you look for where the blue spots are, and those are the places that it's touching. But I don't want to be subject to whatever somebody else has decided. I want to make it only touch at 3 locations. Well, I have an idea. If I use a cylinder, a cylinder and a plane contact at 2 points, and it contacts somewhere along the line that is the intersection between the cylinder and the plane. And so if I do that, now I know, well, let's see, let me turn that over for just a minute. If I put this along here, now instead of thinking that the contact could be anywhere on this surface, I now know that it's somewhere along that line. Okay, that's good. I know more about where they're contacting. But is this deterministic? Well, the other contact is probably along this line somewhere. But in fact, if they are all rigid bodies, which is a big assumption, but if they are all rigid bodies, it turns out that it cannot actually touch on this line and on the line along this edge. I mean, it could mathematically. There is one position where it could, but it is very unlikely to touch along those two. So I don't actually even know very much about it. And if I set that off to the side, that sort of shows the point. I can either have it straighten itself out. I can either have it so it is contacting along the line of that dowel pin, or I can rock it back and it's contacting along the line of this edge. Well, that doesn't help me very much. But wait, I can, and the other problem is that there are actually 2 solutions to this, even more solutions to this, because it could be contacting on this side, or it could be contacting over there. And so this is not a very deterministic setup. Now this is sort of a macro level of what's happening at the micro level down here, where I don't know what contact points are, and in fact, I don't know if you'll be able to hear it, even though these are pretty good surfaces. I can rock this part back and forth by pressing on these 2 corners. It is a little tiny bit of rocking, but I can tell that there are 2 solutions here. There's one with this corner down and one with this corner down. Okay, how can I make this better? Well, one thing I could do is I could use 2 cylinders, because now what I've done is I've taken the I've taken the contact and put it along a line on that cylinder and along a line on this cylinder. Okay, so that's way better, right? I've taken it, it used to be that the contact was happening somewhere along this entire surface, and now I've reduced it to these 2 lines. So I have increased my determinism. I know a lot more about where it's contacting. But do I know where it's contacting? Not really. At some point, I think you can hear that. It is wobbling back and forth because it's still not deterministic. There are still two solutions. Either it's in contact with this entire dowel pin and one point on the front dowel pin, or it's in contact with the front dowel pin and only one point on the back dowel pin. Well, to increase determinism, one thing I could do is I could take this front dowel pin, and instead of making it long, I could make it really short. And what I've done is, instead of having a long potential contact length, I've reduced it even more. So I've made it more deterministic. Now when I put it on, maybe it rocks just a little bit, but it's much more deterministic. If I had to say, you know, where are these two contacting? Well, I would say it's along this line somewhere and along that little tiny short line. Okay, how could I make it more deterministic? Well, I could use two little dowel pins back here instead of this one. What we do, we could use individual dowel pins, or we can use one big dowel pin and do what we call relieve it, where we put a slot in it. So let me hold that up so the camera can see. That's had a smaller diameter machined in this part of it. So now I know that it's going to contact along this length and along this little length and along that length. So I've improved determinism even more. Okay, getting better. And I can, well, I can't feel a wobble in that one. So my determinism is getting better at each one of these steps. And so I hope you see some of what we mean by improving determinism or increasing determinism. When we get to the point where we touch this, these two, and we know exactly where on this surface the two contact each other, then we have complete determinism. And so, but there are some downsides to getting it too small. If we go to an infinitesimally small point, remember that pressure is force divided by area. If I have an infinitesimally small point, my area will be very, very small. And if the area is very, very small, then the, so if the area is very, very small, then force divided by a very small number gives a huge number. That means that our pressure is really big. And if our pressure is really big, remember that pressure is the units of stress. And so we will exceed the yield stress, and instead of positioning this part, we'll just deform this part. And so we can't go to infinitesimally small contact points. We have to be somewhere in the middle. And so that's what we're doing with the determinism on all of these parts and throughout this class, is we're trying to determine what level of determinism is good enough. Sometimes being just two flats together will be good enough. Two flats put together, it's not deterministic completely, it's contacting at 3 points. I don't know exactly where they are, but sometimes that will be fine. Sometimes we'll need to do something like go to the cylinder on the plate, and that cylinder on the plate, then that will be good enough. Sometimes we'll need to go the extra distance and go to a relieved cylinder where we're reducing the amounts of length. Sometimes we will need to go to hemispheres, and we will touch it on hemispheres because the hemisphere only touches this surface in a single location until you get a little bit of deflection from the load, and then it's a small circle rather than just a single point, but it's still very well controlled on the end. And so we'll use a couple of little hemispheres down here to position something. So that's determinism, and you should check the assignments because there's probably an opportunity for you to show your understanding of determinism. All right, so I will see you in the next video where we're going to figure out, okay, how do we apply this? How do we determine if something is, it has its degrees of freedom removed?